Good. Well, we'll go ahead and start. Actually, I just wanted to repeat something I mentioned last lecture, but maybe some of you hadn't started the homework problem where you implement an infeasible start Newton method. So I'm just going to repeat it because it's actually super important. It's this, that the gradient and Hessian, you just write out simple formulas for them, like, the gradient is a vector that looks like entry-wise 1 over x, right? And the Hessian is diag of like 1 over xi squared or something like that. So the problem is that those make sense when the xi's are negative, those expressions, right? They parse. I mean, if you're unlucky enough to have one of the xi's 0, then both of those are going to give you some trouble. But they're going to make sense. They are completely wrong and have no meaning whatsoever in this problem, right? Because for us, the function is defined on x positive, period, right? So what that means is in your line search, you're going to want to first make sure that x plus tv is positive. And you keep reducing, or you have t times equals beta until that becomes true. Then you check the residual. Unfortunately, if you go ahead and check the residual, it's very likely to actually make sense. And everything will be wrong. Nothing good is going to happen after that. And it's going to be a disaster. So, okay, I feel like I've said it enough. So, okay. The other thing I was going to say is, if you get it to work and and you have some extra time, probably you don't, but it wouldn't be very hard for you to then make a new version that uses sparse linear algebra. You can't do that in NumPy. You're going to do that in SciPy. So, and this is just for fun. This is just if you wanted to. Actually, by the end of next week, it means you'll have implemented an LP solver that will solve 10,000 variable problems, which is kind of cool, I think. So anyway, that would not be very hard to do. That's just if you, I know a bunch of people are interested in this. If you want to, this would be a great practice to do that, would be to implement a sparse-friendly version. And the only difference is that A is sparse then, right? The matrix A. And then the only other thing is you just go through the code and replace the NumPy. You could actually do a direct KKT factorization with an LDL transpose. You could do all these sorts of stuff. But this is only if you want. So, okay. Any questions, or how many people here have actually attempted it so far? Okay. And how many actually have it like working? Awesome. Okay. And for the rest of you anyway, I think that the number one bug is the one I just mentioned, is the domain issue. So, okay. Oh, and the other thing is, of course, I think I mentioned this last time, but please have the sense that if you get into like the 3-hour thing, 3-4 hours of attempting to debug this, unless it just becomes like a weird obsession and matter of personal pride, which it kind of should, but if it does, barring that, you should have the sense to quit, right? Because at some point, because that's kind of not the point of the class, is not to debug, optimization scripts anyway. Actually, the main point of this is to demystify how these things work. So by next week, using the things we're going to talk about today, you're actually going to end up implementing a full LP solver, right? Which is kind of cool. And that way, I don't know how many people can say they've implemented an LP solver from scratch. That actually is not so bad. So, okay. Let's continue. Where we were last time was we said let's take a look at how to handle. So we do know we're going to assume all the functions involved. Whoops, that's no good. We're going to assume that all of the functions involved are going to be smooth. So we have a problem that looks like this, right? And without these, we know how to solve this problem, right? So this we would just apply Newton's method. And several variations of Newton's method, as a matter of fact, right, to solve this, right? So the question is, how would you, roughly speaking, how do you extend it to handle these inequality constraints, right? So that's one way to do it, right? And what you could do is you could do something like put it in the objective. I forget, I guess we typically have M, right? And this is the I indicator function of fi of x less than 0. This returns plus infinity if this is positive, and 0 otherwise, okay? So this would be one version of this. And here's this function I right here. It's the indicator function of negative numbers, right? Okay? So let's actually talk about methods you might do this, right? So here's one. And I could tell the story, I could make it pretty persuasive, the story I'm about to give, right? And it goes like this. You finish, you debug your Newton solver for this thing here, right? You get it debugged, and then someone says, yeah, add this in, because I want to also handle constraints. And you go, cool. So here's a method I'm going to propose. Ready? You just apply Newton's method to this. Okay? And someone said, but wait, this is not smooth. Everybody following this, right? And then you'd say, well, yeah, that's just mathematicians. That doesn't matter. I mean, come on, let's just try this anyway. Everyone see what I'm saying? Anyway, that will fail absolutely miserably. It will not work at all. So this is one of those cases where it's not just a question of mathematicians. It's that there's a real problem there. So that won't work at all, right? I mean, not to mention what happens if you end up at a point that's like infeasible. Anyway, it won't work. Okay. Now the next variation on it is, I'll explain it also, here would be the street fighting method to do it, is someone says, what's your problem? And you go, well, I would like to incorporate this function here, but it's not smooth, right? So I can't use Newton's method. Once this is smooth, I can use Newton's method. And someone says, I got it. You get some sandpaper, and you come over here, and you just sand off the corner here, okay? And now what I mean by that is I can make a completely smooth approximation of that function. And you go, there, I'm good with the convergence police. I mean, everything is cool now. Everybody following this? And guess what? It would work. It's just that Newton's method would take, 100 gazillion iterations to converge. Why is that? Someone explain why.
That doesn't look very quadratic.
That's a good point. Yeah. Okay. Yeah. So yeah, that has a really big third derivative. It doesn't look quadratic and all that kind of. So basically, the smoother it is, kind of the better Newton's method is going to work. This is kind of just intuitive, but that's the idea, and that's exactly right. Okay. So this story starts that way, but it's actually instead going to have a happy ending. So the specific approximation it's going to be used is something called the logarithmic barrier. So, and we can, it's going to look like this. It's these functions. So here's the actual function, this indicator function, and then this is basically -1/t log -1/. They all go through 0 here at -1, right? They get slightly negative here, and then they go up to plus infinity as you approach this boundary. Okay, so. This thing that's like Newton ready, right? That's a smooth problem, smooth objective, equality constraints. The code you're going to implement will just solve it, right? It literally will solve something very close to this, right? So in your homework, so that works, okay? So the idea is this is an approximation of this indicator function, and what's clear is t is like a parameter, which tells me how good an approximation how good an approximation I make. If t is really big, I get something that looks like this, right? And intuition suggests that then I would get a really good approximation of the original problem. And by the way, we're going to see that that's true, and we're going to make that very explicit momentarily. But the point is, that's what the intuition is. On the other hand, what would you predict about the value t and Newton's method? What happens as you get t bigger and bigger here? Well, so basically, you should, before we even get into this, think, here's what's going to happen. As t gets bigger and bigger, you will indeed get a better and better approximation of the original problem, number one. Number two, Newton's method will take longer and longer to solve, right? So that's what you should be thinking. It's actually true. Okay, the question is just, how do these two play together? Okay, so this is the story. And I do want to point out also, that the story sounds similar to another story that started the same way. That was the Lagrange duality story. Now, that was even more absurd, right? That was, I'm going to approximate this function by this, right? With a slope lambda I. So that's the Lagrange story. Now that had a happy ending. I mean, you have to interpret it exactly correctly, right? But that one actually weirdly kind of worked, right? These are actually like good, reasonable approximations, right? I think you'd have to say that a line here is not, right? So, oh, it's called a barrier because this function, it actually requires you to be strictly feasible, right? And then you've got this function that goes to plus infinity. That's a barrier function, or yeah, that's one name. Now, by the way, there's a whole other version of all this which you can do, which is a so-called penalty function. And a penalty functions look like this. Let's toss this out. Penalty functions go like this. They kind of do the opposite, and then they start going up rapidly. So this is a so-called penalty function, right? So penalty says, I will, and then I could make this steeper and steeper. That would be my parameter that tells me how good so this would give you an outer bound, right? The other one gives you sort of an inner one, right? Okay, so, and you could develop a whole theory with that if you wanted to. It's fine. Okay. So this log barrier function, right? It's the sum of minus log minus fi. And I mean, it's of course convex, right? And we'll write down what its derivatives are. So the derivatives are basically, it's the sum of the gradients of the functions then scaled, right? Fi of x is negative, right? So that's this thing, you should interpret this as the margin, right? And the Hessian has two terms, right? It's got the second, it's got the Hessian of the individual functions, right? Scaled by minus fi, which is 1 over the margin, which is non-negative, right? And then it's got a bunch of rank 1 terms, which has to do with the gradient, and that's scaled by 1 over fi of x squared, right? So that's, which is basically the margin, the square of the margin, okay? So these are what these two things look like, right? And again, all sorts of stuff should be, you should be storing in your mind for possible exploitation, like, diagonal plus, low rank or something. Okay. So what we do is we're going to multiply through the t. It had been 1 over t times phi. We just put the t over an f0. It's the same. It's equivalent problem, right? And now what we're going to assume that problem up there has a solution for each positive t, right? So we'll just assume that. And then what that means is we can actually parameterize it by t. And so you get something you get this thing which is like x star of t. It's the solution of this problem as a function of this parameter t. So that's what it is, right? So when t is, well, let's see. Okay, yeah. Well, we can go through this. As t goes to infinity, we imagine this to be a really good approximation of the real function, which is like, f0 plus then the indicator function of all of the all of the constraints, right? So this gives a curve in Rn parameterized by this parameter t, this thing, and this is called the central path. This curve. So that's the name of it. And here's just a baby picture to show you what it looks like. So here's a polyhedron here. So the original problem was an LP. These are the constraints. Let's see what happens when I set t equals, very small, like 0. I'm minimizing that log barrier over this polyhedron, and that's going to give me, it's going to start at the analytic center. So that's going to be the analytic center of this, right? So, and in fact, if you'll recall, this point maximizes the product of the margins here, right? Which is the same as maximizing the sum of the logs of the margins. Okay, now as t gets bigger and bigger, I'm bringing in t c transpose x because that's the objective here, right? And what happens is it moves along here, and you can actually work out exactly what happens, right? When I choose, this is of 10, what's going to happen is this is the optimal point. C points this way, so the whole LP says, please go as far as you can this direction in this polyhedron, and that's the optimal point, right? And so here is the so-called central path. And you can actually see what happens as this is when it's 0, this is when it's 10, I don't know, this is maybe 20, 30. But as you increase t, this is indeed, it's a 2D example, so it's kind of silly, but it is indeed moving towards an optimal point. Well, in this case, I can say the optimal point, right? So that all kind of makes sense. That's the idea. Okay, so this is the picture. Now, of course, you have to visualize this in 1,000 dimensions really to understand how all this works and stuff like that. But this is a good enough picture to get the idea. Okay. Something very cool happens, and that's this. If you are on the central path, then it means that you solve this problem right here. You solve this problem. Well, the KKT conditions for that are going to be AX equals B, that's primal feasibility, and then, T grad F of 0 plus grad phi plus A transpose nu, and that's going to be the equals 0. That's going to be the dual part of the KKT conditions. And so these are the optimality conditions. And here I've simply expanded out let's see. I have expanded out the gradient of the barrier, and it looks like this thing here, right? So it looks like it looks like that. So okay, it's that's fine. But if you stare at this very, very closely, if I tell you that this is 0, and I look at the coefficients here, I divide by t, right? So that's grad of 0. This is 1 over minus t fi of x. That's a positive number because fi of x is less than 0, right? That's required here. And I see that, hey, look at that. When x star of t satisfies the gradient of f0 plus a sum of positive numbers times the gradients of fi plus A transpose W is 0. And then you think about that, and you think about it in your head, and you say, oh my God, that means that this thing actually minimizes the Lagrangian, but for these specific choices, right? So nu is W over T, and the lambda i's are 1 over T times the margins. Make sense? Okay. Well, this is kind of cool, because if you have a dual feasible, if you have a point that minimizes the Lagrangian, that means you just evaluated G, the dual function. And if you evaluate the dual function at this particular lambda and this nu here, you just work out what it is. It's just the Lagrangian of this. And when I plug in what it is at lambda star here, if I plug that in here, I get something actually kind of amazing, because you'll remember that each of these is that. So when I plug that in there, the FIs just cancel, period. They cancel, and you get like basically minus 1 over T. You add up m of those, and you get this term. And so you get something amazing that looks like this. So let's actually read it. It's super simple. It says that this is the current value. This is the current value. X star of T is strictly feasible, right? So this is sort of an upper bound on the optimal value P star, right? What this says is that if you subtract m over t from it, that number is less than the optimal value. Another way to say it is that the gap between your value and P star is less than m over t. Okay? So that's actually, so let's go back and see what that says. That says that if you simply solve, let's see, if you solve, I'll find the, here it is. So if you simply solve this problem, which you know how to do because you just use Newton's method, then two things are going to happen. Number one, you will, whether you like it or not, you're going to inadvertently produce dual feasible points. Those dual feasible points are going to give you a bound on P star. Not only that, we know exactly the gap. And the gap is defined as the difference between your current objective value and your best and P star. It's exactly m over t. Right. And so that's actually very cool. It completely confirms all this like hand waving about if T gets big, right? I mean, here would be my hand waving is, yeah, sure. If T gets big, that approximates that. That's got to be close to the real thing. But this is just very simple. It just says when you compute a point on the central path, you will find actually a primal point and a dual and a pair of dual points, and the gap is going to be m over t. So if T goes to infinity now, you solve the problem. And that's completely clear. Yeah?
What is the Difference between doing it this way and just starting by taking the Lagrangian of the original problem and doing it like from there?
Oh, yeah, that's a great question. For many problems, I mean, LP would be a perfect example, right? If you just pick, random dual variables and you evaluate the dual function, you get minus infinity, right? Because, for example, for an LP and for many problems, the dual function is minus infinity unless some very specific things happen, like equality constraints hold, right? So if I say, here's my LP, and you say, oh, fine, I'm going to form a Lagrangian, then how do you pick your dual variables, right? The answer is if you're doing it randomly or something, you're just going to get, congratulations, your lower bound is minus infinity. This is very cool because this says you solve a smooth, equality constrained problem, and then out of that is going to come some dual variables that are guaranteed to be dual feasible. And you'll get not only will you get a non-trivial, in other words, a not minus infinity lower bound, you're going to get one that's actually the value you get minus m over t. I don't know if that made sense. So here you are finding the dual variables inadvertently by minimizing this barrier function, right? There are problems where, if the domain of G is everything, where you can just update the dual variables and stuff like that, right? So actually those are often called either price-directed methods. That's in economics, that's what they're referred to, right? But it doesn't work for most problems. If you have an LP or something, it doesn't work at all. Because those, roughly speaking, those prices have to satisfy extremely specific properties, right? So, okay, good. Okay. Now we can also interpret this via KKT conditions, right? So let's see how that works. Okay, so if you look at x star of t, that's the thing you compute by Newton's method. Well, in fact, I think the verb you would use is you've actually centered, or you've computed a point on the central path, right? You've computed x star of t here. And then from that, we get these lambda stars, right? These 1 over t times the margins and blah, 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 right? So I get those. And they are also functions of t. I think, yeah, that's fine. So we do that. And now this is a primal dual pair. And let's see what they satisfy. Well, not only do they satisfy this, these are actually satisfied with a strict inequality, right? Because you have this log barrier, so you can't even be 0, right? So primal feasibility works. The ax equals b comes for free because you solved the problem with the constraint ax equals b, so that's free. Your dual constraints are, well, these are definitely bigger than or equal to 0. As a matter of fact, they're positive if you look at what those numbers are. They're 1 over the margins times t, right? And t is positive and the margin is positive and all that. So in fact, this inequality and this one hold with strict. They're strict. But this is all we really want here. If you go through and work out, well, this is actually by definition, remember that we define lambda I to be 1 over minus t fi of x, right? And so I express that this way. And then the final part is the gradient of the Lagrangian, it is 0, right? So, that's fine. Okay, now if you stare at this and say, what's the difference between this and the KKT conditions of the original problem? There's only one difference, and it's really small. It's right here. This is the complementary slackness condition, and in the real KKT conditions, if lambda I fi were 0, then that would be these would literally be the optimality conditions for the original problem. Okay? So what's happened is you've simply replaced them with, instead of 0, you have 1 over t. T is positive, and as a matter of fact, t is going to get bigger and bigger. So you're actually saying, well, you're actually computing points that satisfy all the KKT except one, and then it almost satisfies it, especially when t is large. Everybody got that? So that, in fact, I think a lot of derivations of this start that way. They say, here's the KKT conditions, you put a 0 over there, and they go, okay, we're going to replace 0 with 1 over t. And then you're like, well, then how would you solve this, right? But now you know, right? You solve it by doing this centering problem. Everybody following this? So it's a very good, beautiful interpretation. There's also really cool, like you can imagine, a force field interpretation, right? So forget the equality constraints just to make this simple. But so we're going to minimize this function here, right? And what I do I'll think of a mechanical interpretation, right? So I think of X as like a generalized position or configuration or something like of some system, right? And then what I do is I have so this thing is going to be the potential of some force field. A force field is the negative gradient of a potential, right? So what I do is this is that's my force field. And then here I have that's the potential of a force field associated with each constraint, right? And at this central point, the force fields, all the forces balance, right? It just means the gradients sum up to 0, right? So that's the picture. And let me show you. I'll just show you some pictures about how you can look at that. So here's an LP, and the way we're going to solve it is this. We'll introduce a force field which is just minus t times c, right? So it just means it's a constant force field. It's like gravity, except it doesn't happen to be pointing straight down, right? It's pointing in, actually it's the force is pointing actually straight in the negative c direction, and it's constant. Oh, multiplied by, if you fix t. Everybody got, so that's just a constant force field. Then for each of these constraints here, what we have is a repulsive force. In other words, if you're here, it's always pointing directly away from these things. In fact, that's what it is. It points directly away, and it's inversely proportional to, I could say the distance, right? To the distance or the margin, right? So what that says is associated with this constraint. This constraint says don't be over here, right? And what the contribution to the force field is as a force field, if I'm right here, it's extremely strong and pointing this way. If I'm way over here, it's very mild, but it is pointing directly away from here, right? So as you move closer here, you get a much stronger force field. This is only if this helps you visualize this, good. If it doesn't, that's fine too, right? But just to get the picture, right? So here at this point, that's t equals 1. We have, I guess in this case, we have, let's see, 1, 2, 3, 4, 5 constraints. So these are the forces associated with the constraints. This is minus c. So I have a constant force, which is, oh, by the way, the objective force is constant everywhere in here. It just says, please go in this direction, right? I mean, I can multiply it by, I'll multiply it by t, which will scale up the effect of that, right? So, okay. And here, so this here is the repulsive force from this constraint. This is the repulsive force from this constraint here, right? This is the repulsive force from this constraint, right? And then, I don't know, you could work it out. I mean, it's true. All of these forces balance at this point on the central path, right? And so now you can see all sorts of cool, you can actually kind of visualize what happens when I increase t, right? When I increase t, this force here, I multiplied it by 3, it gets 3 times stronger, pushing you in this direction. And so it settles to a new equilibrium, which is there. I mean, you can see it along the central path, and everything makes sense. You move this way, and as you did, you got closer to this, and then this got bigger, right? You got closer to this one, this got bigger, and then whatever it is, these 6 force vectors are going to add to 0. So I don't know if this is helpful or not for people, but for me, I think it's a very good way to see this. Okay, let me ask a question about it. What if I take what if I add a redundant constraint to an LP? So I add a new vector A transpose X less than or equal to B, and it's redundant, meaning that visually it means it's like, it's over here. It says, please stay on that side, but everything already in here is on that side. Everybody got that? So here's my question for you. Does it change the central path? Oh, another way to say this. Do redundant inequalities have an effect on the central path? That's my question. What do you think?
No.
Okay. What's your argument?
They're redundant.
They're redundant. I like that argument. It's okay. So here's I like your argument. Okay, it's brief, so that's always a plus. Let's see. Okay. It does have one disadvantage, also brief. It's false, right? But it sounds good, and it's good. Okay, so look, here's what would happen. I mean, let's even think about what would happen, right? What if I shoved an inequality here, and I put a whole bunch over here, right? Each of those is producing a force. Now they're not inside here but it's going to feel this. Suppose I put like 10 constraints right here. Someone tell me, what do you think the central path is going to look like then?
Curve more downwards.
Precisely. But it's going to still sneak up to the solution, right? Because there's all these repulsive forces this way, so it's going to actually do something weird like go along this way, right? But the same story is going to happen. It's going to converge to the solution. Okay. Okay. So again, this is just for interpretation, so you understand how these things work. Actually, when we get to actually see how they work, no one understands how they work. So, but if you want to pretend to understand how they work, this is a good picture to do that with, right? So, okay. Okay, so this brings us to the barrier method. Actually, before I do this, I'm going to talk about another method before that, and it's historical. So, by the way, some of the history is that a lot of this was worked out actually in the 1960s. It had names like barrier method, and I had also, actually, the famous method is something called SUMT, S-U-M-T, is sequential unconstrained minimization technique. That's from the 60s. It was discovered that someone named Deakin in the Soviet Union had worked out actually a completely modern algorithm for all this in 1967. And I guess my friends in Moscow said it was hardly known, or he said it was ignored by people in Moscow. He said, and unknown in the West. That was anyway. It was actually everything that 2 decades later was going to make it to the front page of the New York Times was in this 1967 paper by some guy in some hick province or way off somewhere. I don't know where it was. Okay, so all right. So then in the U.S. there were people, Fiacco and McCormick had come up with these things called the sequential unconstrained minimization technique. So let me explain what it is. Let's go back. And well, actually, I guess you already know all the story, but it goes like this. Now that we know, when you know how to solve that problem up there, it's just Newton's method. You know how to do it. When you do it, actually, not only when you solve that problem, you'll get an approximate solution of the original problem, but with a very strong approximation, you're going to get both a primal and a dual solution, candidates. And the associated gap is going to be exactly m over t, right? So in some sense, you're just done. Like, that's done. You just say, did you want to solve an LP? Then I'd say, to what accuracy do you want to solve it? And someone says, 1e minus 5. And I go, cool. Then what's your m? And now I choose t. And it's an approximation that comes back with a certificate certifying its accuracy. Everybody got this? So, and that, it doesn't have a name, but I would call it UMT, for unconstrained minimization technique. And it's just, all it means is you approximated, it's basically back to that story originally where we approximated this indicator function here with something smooth, then we applied Newton's method. But the nice part is we got a lot of cool stuff there where we know if you use log barrier and all that kind of stuff, you're actually going to get dual feasible points and you get a gap and you know exactly what the gap is. Everybody see this? Yeah. So actually, hilariously, that method is perfectly good for tons of practical problems, right? So just so you know. Of course, it's not generic. You have to choose the t very carefully. And everything you think about it is right, that if you choose t too large, the larger t is, the better approximation you get. Smaller, but also the larger the number of Newton steps it's going to take to solve it and all that kind of stuff. Okay, everybody got that? So that's UMT. Okay. All right, so if you ask for high accuracy or even modest accuracy on something like an LP, then the problem is it's going to take a couple of hundred Newton steps or thousands or something like that. And not only that, probably with numerical errors, it's probably not even going to converge, right? But if you did it with infinite precision, it would, right? Everybody following this? Okay. Okay. So then I have to tell you about something else, which is the background. There's a whole class of problems in applied math and computation called homotopy methods. I don't know if people heard about this before from somewhere. Okay, this is an awesome thing. Everybody should know about this. It's a very, very cool idea. It's this. You have a problem you want to solve, which is either like an optimization problem, but typically it's actually just solving a set of nonlinear equations. You just want to solve. Here's an example, right? You're doing a SPICE simulation, and you want to find an equilibrium point of the circuit, which is, got the DC, whatever. I'm sorry, I'm speaking dialect now, but that's what you want to do, right? So that's a perfect example, right, of this. But it comes up in tons of other stuff, right? So okay. So here's how it works. You have your problem, and you introduce a parameter. They usually call it maybe theta or something, but they have different kappas, another train of, anyway. But here it's t. You introduce a parameter. In fact, in the classical version, you introduce a parameter with the following thing, that perturbs or simplifies or smooths out your original problem. And when you turn that knob, the traditional range is 0 to 1. When I'll use the parameter t, right? When t equals 0, when t equals 1, you get the problem you really want to solve, right? That's the one you really want to solve. When t equals 0, you get a problem that you know the solution to, right? Everybody following this? Now you do the following. Oh, and then what you do is you attempt to solve the problem for t's, and you're going to march along this path. Oh, and by the way, the subtitle of a book on this is called, this is a great subtitle. It's called Homotopy Methods, and the subtitle is Pathways to Solutions, right? Which is like, wow, that's like almost poetic. That's what it is, right? So the idea of a homotopy method is you start with t equals 0, you know the solution already, right? Then you crank t up a little bit and you attempt to solve the problem. And if you solve it, this isn't in general case, right? If you solve it, good for you. Then you crank up t again and you keep going. And when you get to t equals 1, you solved your problem. Oh, and what you would typically do is, let's say you're using Newton's method each time. Each time you would start Newton's method from where you were before. That's the key. Everybody got this? Right? So, matter of fact, this is exactly how SPICE, for those of you who, actually, how many people know about SPICE or have used it or something? Okay, so fine, so some. That's precisely how it computes an equilibrium point. So here, okay, so if you don't mind, for everyone else, you probably get some of this, but I am going to go into dialect a little bit for a while. If you have a circuit, suppose I have a circuit with a bunch of devices, and these are all nonlinear, right? So all you want to do is solve a set of 1 billion nonlinear equations, right? And those equations are things like KCL, KVL, and the device, and that the device, and I guess, yeah, you have to satisfy the device equations, okay? I mean, I think this is fine for everybody to understand, right? So basically it has to satisfy physics and the devices. The physics is linear, by the way. It's just actually conservation of current and all that kind of stuff. That's fine. It's the device equations that are nonlinear, right? Okay. So, I don't know, someone who knows circuits, do you want to guess so I give you a circuit. It doesn't have to be a billion. It's an op amp. I got, 15 device transistors in it, or, devices. And I'd say, please find me the equilibrium or bias. That's dialect. Bias for the equilibrium point. Everybody got this? Okay. Can someone guess a homotopy parameter? This is just for people who know about circuits and circuit design. Okay, I'll tell you what it is. It's the supply voltage. If I take a circuit and I set the supply voltage to 0, your specialty could be genetics, and I think you could probably you could say what the solution is, right? In other words, if I take a circuit and I don't apply power to it, then here's the solution. Ready? All voltages are 0. All potentials are 0. All currents are 0. And that will actually satisfy the equations. Everybody following this? So now I crank up the supply voltage. And again, sorry, this is going to be only for people who know about circuits. The supply voltage is like 2 volts. I set it up to 50 millivolts, and I attempt to solve again for an equilibrium point, right? So I mean, what does any chip look like when I put when I put the supply voltage to 50 millivolts? It looks like it's a resistor, right? Because you don't have enough you don't have enough voltage to actually turn any transistors on. Everybody, I mean, okay, if you know devices, you know what I'm talking about, right? Okay, is linear, but that means we can solve it in like 1 or 2 Newton steps. In fact, the tradition is 1. Okay, then you set it to, 100 millivolts, right? And you keep going until you get to whatever 2 volts, and then you say that's where I have it. Everybody got this? So, okay, so these are homotopy methods. This is super cool to know about it. Okay, this is a homotopy method, but there's a big difference. Here, I can get to any point on that path from anywhere, which is false. And in a general homotopy method, you have all this logic about what happens if you fail, right? Oh, let's talk about that. Suppose t was 0.05, and now I set it to 0.1, and I tried Newton's method, and it just completely failed. What would you suggest? Perfect. 0.075. I totally agree. That's exactly what you do. It means you were too aggressive, right? And you moved too far, and the problem got so different that from where you are, you couldn't get to this thing, right? Okay, so that's exactly how those work. Also, in the general case, all sorts of sick things can happen. Like they're called bifurcate. So 2 very bad things can happen, which is if you're following a path. This is in the general case, which is not ours. So here's a path, and one bad thing that can happen is it can so-called bifurcate and go like this, right? So that's one. Another one is a path can just look like this and just stop, and that's it, right? There may be another one that goes all the way to the solution here, right? So these issues you don't have here because we have a single path. We can get back to it from anywhere we like. The only question is how much effort, how many Newton steps it's going to take. So I don't know if that made sense, but that is the idea. Okay. So now you will recognize this as a homotopy method. So here it is. It says you pick some t and you compute x star of t. That's Newton's method. Then what you do, you quit if m over t is less than epsilon. That's fine. Otherwise, you increase t. This is a very simple method. There's much more sophisticated methods, but this is the way you do it. You just increase t by mu, right? And so mu is this number that tells you how much actually, since the gap is m over t, mu actually is telling you how much are you going to tighten the gap requirement in the next step. That's what it tells. So if mu is like 1.05, I mean, basically the argument would be you just calculated the analytic center at this point. When you increase t by 5%, it hasn't moved very far. Another way to say it is you're just about to solve a problem that's very similar to the one you just solved. And in fact, it's going to take 1 or 2 Newton steps. Okay? And in fact, I think there are some methods that increment t in such a way that it's so small, the increment, that 1 Newton step is all you need. So you do 1 Newton step and increase t, then 1 Newton step, and so on. So that's one way. Those are called short step methods, I think. Okay, everybody got this? Okay. The luxury we have is the following. This algorithm cannot fail for us. I mean, it might fail for numerical reasons, but in theory, it cannot fail. It always works. So it just does. Right, because no matter how aggressively you update it, Newton's method is going to solve this smooth problem. It may take a lot of iterations, but it's going to do it. Okay, okay. So this is the idea. Okay, so it turns out, actually it depends. If you talk to the theorists, mu is going to be really small. Like it's going to literally be like 1 plus 1 over m or something like that. Right, I have no problem with that. Turns out in practice, people will choose things like 10, 20, 50, or 100, something like that. It's really quite large values, right? Okay, yeah, and there's plenty of heuristics for choosing t0 and stuff like that. But okay, so that's it. This is the barrier method. Okay, the convergence analysis is actually kind of interesting, and so it works like this, right? Every time you recompute a new point on the central path, the new gap went down by a factor of mu. Because actually that mu is just controlling like how much you tighten your gap each time. Right. So what's interesting about this is there's no surprise after the end of an iteration what your gap is, right? Your gap is this provable distance between how far you are and the optimal value is. And you can imagine a lot of algorithms go like this. You finish all your calculation, then there's a drum roll, and you evaluate the dual function, which is a lower bound, and then you look up and go like, oh my God, that's awesome. I'm already 1%, I'm provably 1% suboptimal, and I've only done, blah, 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 22 iterations. Everybody, so that's how usually, here, there's no surprise. The gap will be, period, m over t. So you basically dial in the gap. That's how that works. Okay. So what that says is that every time you do a centering, you reduce the gap by a factor mu. So that says that the number of iterations it's going to take is like an original gap divided by log mu, right? And so that's going to be that's the number of iterations you take, right? Now the centering but then remember, you have to do the centering, right? And the real measure is like, let's say we could use how many Newton steps do you actually end up performing, right? That would be one way to do this. And if you do the classical analysis, what you get is something very weird. It goes like the classical analysis says, oh yeah, I can minimize this for you. No problem, right? I can minimize that. And you get a Lipschitz constant and a strong convexity and blah, 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 and you do this. But what the classical analysis will predict is that as t gets bigger and bigger, the classical analysis will tell you that the number of Newton steps will grow. And in fact, it'll grow like alarmingly fast, okay? And then when you work this out, you realize it just doesn't, if you're a theorist and you assemble all these things together, you'll find out, it's going to grow really fast, right? And it won't get you what you want, which is like a polynomial time method. Yes?
What happens if you don't always solve the minimization problem fully? Because you just need a better point, right?
Yeah, so no, that's exactly right. So when you're centering, for sure, the last two Newton steps were completely a waste of time, right? So, and in fact, real methods don't do that. You never solve it directly. By the time, as a matter of fact, what they do is by the time you're in the region of quadratic convergence, t gets updated then, right?
So once you're there, you're
well, it's silly because
let's
let's draw that picture, right? So that picture looks like this, right? Here's the central path, right? You're here, you're going here. Here's your Newton steps, right? First you go like here, here, I'll make it take a couple more steps. Here's what, goes like that. But then you get close, right? And now you do two more steps that we can't see here on the board, right? And so, these are a complete waste of time if you think about it. Because someone says, what are you doing? You go, well, I'm going back to the path because I want to be on the path with double precision accuracy. And someone's like, dude, what is the path? I asked you to solve an SOCP or a quadratic program. So what is this path thing? And why should I care? And the answer is you shouldn't care because the path is just a construct for us to figure out a way to get to the solution, which is over here, right? So in fact, all the analyses work. And in fact, if you have fancy methods, they will not do this, right? But in this method, you do that and you're completely right. The last step or two or three are just completely wasted. So, okay. That was a question.
In practice, how much of a gain does this centering give you rather than just starting with a very large t and solving it with that?
It's usually infinity in practice, right? In theory, it's not infinity. It's just unbelievably large, right? And the reason is in practice, what happens is if I say solve my LP to 6 significant digits or something, right? Then you go no problem. T equals 1e plus 7 or something. Write that. Now, in theory, you could just do it in one step, right? You just solve that one, just run Newton's method now. The problem, what's going to happen then is you're going to get into numerical issues, and it's just not going to work, right? And even if it did work, it would take a gazillion iterations. Yeah. So in practice, it's very considerable. Yeah. So yeah.
I just want to make sure that I'm understanding this offset of m over t correctly. So does that mean that if you only cared about what p star is, you could just solve the problem for 1t and just add the constant?
That's correct. Right. That's what I call the UMT method, unconstrained minimization technique. That's completely correct. Yeah, that's right. Right. What this says, I guess that question was what happens if you do that, but then someone says, I want 1e minus 7 accuracy. And so they go, no problem, t equals, 1e plus 9. It will work in theory, but I mean, numerically at that point, it's not going to. I mean, that corresponds to the person who comes over here, takes this thing, right? I mean, t equals 1e plus 9 corresponds to basically to someone who just says, give me some sandpaper, sands off this rough corner and says, done. It's smooth. Go ahead. Use your Newton method. Everybody following this, right? So we know now the theory is that that will work, but it will take a lot of iterations. And the practice is that it will take, number one, it'll take a gazillion iterations or most likely just fail, right? So, okay. Okay, everybody got this? So the classical analysis actually tells you that as t gets bigger and bigger, it's going to take you more and more Newton steps to get to recenter, right? And the reason is pretty clear because what's going to happen is t gets bigger and bigger, both that Lipschitz constant and that strong convexity constant are going to scale up. And so, but I mean, that's silly because that's someone saying your algorithm doesn't, if someone said your algorithm doesn't work, you'd say why? And you'd go, well, because my analysis predicts an upper bound on the number of steps that's growing, right? And the point is the analysis turns out to be just wrong. So empirically, it's found that the number of steps don't grow as t gets bigger and bigger. Again, it's critical you start from the previous value. So that's the critical part. And we'll see that self-concordance actually verifies that completely, right? So we'll see that in a minute. Okay. So let's look at some examples. So this is just an LP. As a matter of fact, you are going to implement exactly this by a week from tomorrow, right? So, okay, so let's take, this is the duality gap. That's the gap between the primal value you found and the dual value. So this produces both also, not just a primal value, but a dual, of course, as well, right? And so these are these staircase plots, and let me explain what they are. This is Newton steps. The width of the tread in the staircase is the number of Newton steps per centering. The drop is precisely, it's dividing the gap by a factor of mu. So on a semi-log plot, those stairs have a constant rise, right? Each one. And the rise is precisely 1 over mu, right? Or something like that. In other words, you reduce the gap by a factor of mu, okay? So we can look and we can see all sorts of cool things here. Like, let's take the mu equals 51. Mu equals 50 says you are aggressively updating t each step. And sure enough, look at that. It takes you all of, 11 iterations to do the first centering. The next one takes also like 10 or 11. Everybody see that? That's the width of those stairs. Now, when you do center, the gap goes down by 50x, which is pretty decent. Everybody, right? Here's like little mousy steps. Mu equals 2, right? Actually, it'll be hilarious because the theory will be calling for mu equals 1.0001, but that's another story, right? But if you look at mu equals 2, again, what you see are the treads are shorter. They're shorter because the Newton problems you're solving are easier. Basically what's happening is you've computed a point like here, and when it's 50x, it's like, way over here. You're going to actually have to do some work, right? But when it's 2, it's just over here, and it's going to be like 2-3 Newton steps and game over. Okay? Everybody see this? So you get that. This is mu equals 150, right? So this shows you the number of Newton iterations versus how you choose that parameter mu. And by the way, if you made mu bigger, it would start to go up again. But what you see is something actually, so first, well, let's talk about how weird this is. Basically, if you kept going, obviously this would get to 10 to the minus 8, but let's take that as an acceptable amount to reduce your gap, right? We just reduced our gap by a factor of 10 to the 8. And we did the whole thing in, I don't know, let's look at this one, 37 Newton steps. Everybody, so actually that takes just some thought to sit there and think about what this means, right? So an LP is, you have 50 variables, 100 constraints. When you picture this, it's this polyhedron in R50. with 100 faces. The number of vertices it has is just astronomical. One of those is the solution. Everybody following this, right? So, and what this shows is like extremely embarrassing is that in 30 odd Newton steps, you actually get an extremely high accuracy solution. Let me make that clearer, right? By the way, you get the exact same plots look like this when the dimensions go up. They look exactly the same, right? So, but even here, it's amazing. Like R50 is a pretty, you know what? Yeah, you would get exactly the same plot if this was, 10,000 inequalities and whatever, 5,000. It wouldn't matter. It'd be the same, right? But what this says is actually very, very weird, right? What it says is, if you think about it, you actually do 50 Newton steps. So what that means is, in solving this LP, you start at some point. Literally, you ask for directions. You calculate things involving these barrier functions and things like that, and the equality constraint. Actually, you know exactly what you solve a linear KKT system, and you get a direction. Everybody got that? Then you do a line. Then on that direction, you do a line search, right? Then you stop. That's iteration 1. You're at the new point. You ask for directions again, which is you just query the constraints and the objective, and you construct some KKT matrix and get a new direction and go again. Everybody got this? So let's pretend that was in 5,000 variables, right? So that's in 5,000 dimensions. You stop and ask for directions 35 times. Everybody getting this? I find it impressive, right? Like R5000 is a really big place, right? And so the idea that you actually can do this in like a mere 30 Newton steps or 30 steps, right? I think is just stunning. Right. Okay, so yeah.
In the plot on the right, why are there these little jumps? For example, at 140 it's slow and then 140.
They're just, I don't know, but they're just random perturbations of, because you can accidentally land somewhere where instead of taking some number of Newton steps, you take a lot less. That's that dumb luck phenomenon. So could be that, I don't know. Yeah, I mean, this is presumably on a single instance, right? If we averaged over a bunch, that would, I can't imagine that those bumps would stay there, right? So, okay. This is also extremely important, and what it says is bizarre. If you think about what mu does, mu is the aggressiveness by which you update your homotopy parameter. Or if you like, it's a parameter that tells you how aggressively each step you decrease the target gap. In fact, it is literally that number, right? So then there's a trade-off, right? We discussed it several times, right? If mu is small, like 1.05, you're taking little baby steps. It's going to take 1 Newton step or 2 to recenter, right? But you're only making 5% progress each step. Or you could take, mu equals 10. Good news is you're going to divide your gap by a factor of 10 when you finish. Bad news is it's going to be harder they're going to take more Newton steps. Everybody following this? Okay. So what this tells you, and this is confirmed in lots and lots and lots of other cases, is these two effects basically balance each other. And that is super good, because the last thing you want, what it says is the choice of mu doesn't make any difference at all. I mean, as long as it's within, a factor of 100 of some reasonable value. Everybody see this? So that's very cool. Okay, so this is what that looks like. And I find it pretty spooky, right, that this works. I mean, here's a GP, and again, these are small ones, but nevertheless, that's pretty cool. Here it is. And it takes 20 to whatever, it takes like 30 something iterations, right? Yeah, by the way, something like this would be 25 years ago would just be like utterly unknown. People were still publishing papers on fancy custom methods to solve GPs. So this is maybe 30 years ago, right? So still pretty cool. But these things all just start looking the same, right? So here's what it looks like when you just take, this is actually literally, this is the one you're going to do for your homework. You're going to implement this. And here we have a bunch of values of m, and we are going to solve like 100 different things. What's cool is you look, this is the problem size, right? And this is the number of steps. The first thing you should notice is that it ranges between like 20 and 25, with the absolute maximum being 30. And by the way, if you look at the output when you call the solve method in CVXPy, it's going to call some solver. But if it's something like ecos or something like that, it will actually tell you how many iterations it is. And it's typically between 20 and 50. Right? So in fact, I don't think it's ever more than 50. But this is like kind of stunning, right? Right? And this confused a lot of people. So, first people said, oh yeah, I think it's like the square root. And someone said, no, I think it grows like the log and whatever. And then finally, what has become clear as an empirical fact is that the growth is O of 1. In other words, barrier methods take between 20 and 50 steps, period. And that's just what they do in any dimension. So, and this is, it's been borne out pretty well. So I have oh, by the way, those steps are Newton steps. So what that means is you're solving a linear KKT system, right? So you're solving literally an A transpose A0 linear set of linear equations, right? That's what it is. Now, of course, as the problem gets bigger, that numerical step, that's going to take you more time, obviously, right? So I'm not saying that it takes the same amount of time to solve a 100 variable problem as a million variable problem. What I am saying is that the number of iterations are the same. So I have a friend in Edinburgh who decided to solve some LP with a basic barrier method. And I asked him, like, how many variables do you have? And he said, well, I think we have I think it was something like 2 billion variables. And it was like 500 million constraints, right? And I was like, well, how do you do that? And he had some gigantic computer, a supercomputer somewhere to do all this, right? I mean, this is a while ago, so I'm sure now it wouldn't be that big a deal. But anyway, and I was like, wow, that's awesome. So I asked him, how many iterations does it take? He said, it's the same as, for, real, smaller dimensions. I was like, what? And he goes like 22, 23, always. I was like, oh. So, but by the way, I asked him, how much does an iteration cost? And he's like, each iteration, I think, it was something like, 25 minutes, right? And I added to the story that when each iteration starts, the lights in Edinburgh dim, right? But that part is not true, of course. But anyway, so that was the story. So this picture continues as far as anybody knows forever, right? So this is the number. It's one of these weird, just magic things that practical problems are solved in O of 1. Iterations, but the iterations are going to scale by. Actually, the implication of all this is amazing, because it basically says you're going to solve 20 odd Newton steps. A Newton step is minimizing a convex quadratic subject to equality constraint. It is nothing more than that. It also says, since the number of it is between 20 and 50, like for all problems across all fields and all sizes of problems and all that kind of stuff, that just doesn't change. What it tells you is everything comes down to the linear algebra, right? So that's where so when you do well, it's not because you have a fancy algorithm, because they're basically perfect now. They're more sophisticated than what I'm showing you, but they're very, very close. So actually all the advances are in linear algebra. Right, so that's what that's about. So okay, so this just shows you how this works. Okay, so what we're going to talk about now. So anyway, I think this is just sort of like amazing stuff. Like as I said, so I can tell you a little bit about the history of some of this. So there are precursors of this in the 60s. Including all the way up to developing like codes, algorithms, ones extremely similar to this, right, in the 60s. They fell out of fashion or were ignored or were unknown, right? Like, for example, Deacon's work, right? Just completely unknown, right? So what happened was in the late 80s, early 90s, it was rediscovered. Of course, when it was rediscovered, it was much more complicated, right? Obviously, right? And so people were writing papers, and it was just getting very weird. And it actually ended up on the front cover of the New York Times, right? Because it was It was actually, this was the method used to show that linear programs can be solved in polynomial time, right? Which it had precisely 0 practical consequences because at that point, people who actually solved LPs had been solving them for 40 years at that point, using the simplex method, which worked unbelievably well, thank you. So it had no practical, but it was very funny because it was actually on the front page of the New York Times, and it said that vast numbers of scheduling problems and allocation problems can now be solved, and it was like just completely wrong. Anyway, but it's kind of cool because to see, yeah, I don't know, people I know have occurring on the front cover of the New York Times. Anyway, that's it. So, yeah. By the way, later, some 10 years later, people went back, found the history, pulled up these things from the 60s. Someone even took some crazy Fortran code from the 1960s, untouched, which was on cards, read it in, updated it to whatever it was at the time, to F90 or something like that, updated it, and it was hilariously competitive with the best solvers at that time, which, by the way, it tells you something about academics and things like that, which is, there are fashions, and there's all sorts of stuff that works perfectly well, but people just ignore it and move on out of snobbery or ignorance or something. Anyway, so I thought that was very embarrassing, that for the field, right? So, okay. All right, this is, that's it. Okay, so what we're gonna talk about now is feasibility in phase 1 methods required, actually strictly feasible point, right? What I will say is that the methods people actually use they use something that does phase 1 and phase 2 all together and all that kind of stuff. By the way, if we had one more week of this class, you would actually implement that, because it would be about, I don't know, 5 more lines than what you're going to write. And that one would actually handle feasibility, unboundedness, everything just all at once. So, but nevertheless, this is actually very good to know about because it's got a lot of uses just by itself. So here it is. So the feasibility problem is, find an X that satisfies a bunch of inequalities and maybe some linear equality constraints, right? And so the classical method, they call it a phase 1, phase 2 method. So phase 1, find a feasible point. Phase 2, run an algorithm to find an optimal point. That's how, and this is kind of old school, but it's not, you might someday encounter, people who were trained in old school stuff. And then if you say it around, a lot of people today, if you say phase 1, phase 2, they're like, what are you talking about, right? So, but it's possible you'll meet some of these people sometime. And the ideas are very interesting. Okay, so here's what you do. What we do is we put here a slack variable s, right? And we want to minimize over x and s this s. Now what we do is we terminate this the minute we produce something with s negative, we quit. Because at that point, what you've done is you've computed a strictly feasible point, and then you jump back to the barrier method. Or actually, you can apply the barrier method to this. Because here I know a feasible point. It's like you pick your favorite point, x, that satisfies ax equals b. Okay, it has to be in the domain of the fi's, but whatever. What I do is I evaluate fi of x, all of them. I take the max of those numbers, plus 1, and that's my initial s. It's feasible, right? And so this would just work. Okay, so that's that. But let me ask a couple of questions. So let me ask what happens if these inequalities are not feasible. Then what's going to happen is when you solve this problem, you're going to get s equals like 1.3, and that has a beautiful interpretation. It basically says your inequalities are not mutually feasible, because they're all fi less than 0. But if you relax those and everyone looks like fi of x is less than 1.3, I got a point for you. Everybody following this? And so you're kind of, basically you can interpret this basic phase 1 method as minimizing the maximum constraint violation, right? And now I'm going to ask you a question. Suppose a set of inequalities is not feasible. And here's what I want to know. I run this. S star turns out to be 1.3, let's say. I want you to tell me about what do you think the FIs look like? This is just a guess, right? I mean, what do you imagine?
Quite a lot of them will be at that area.
That's exactly right. That, basically, I mean, you kind of, if you're anthropomorphizing this, right? You have all these functions here. You want them all to be less than 0. So what you do is you just put a big old flat thing on top of it. That's S, and you just push down. You push down until it locks, and it's pushing back harder than you can push, right? In fact, with infinite thing, right? So you can actually make a mechanical interpretation if you wanted, right? Everybody see this? Now, when this thing locks and you can't push it down any farther, there's going to be at least several, and in general, a whole bunch of constraints violated by 1.3. Everybody got that? So, and that, there are applications where that might be of interest, right? You'd say, I have a whole bunch of constraints, and you'd say, well, I got good news and bad news. Bad news is there is no X that satisfies all your constraints. There's no design that meets all your specs, right? Good news is if I only relax all of them by 0.3, then it's feasible. Everybody see this? Right? Okay, so that's the idea there. So if you do, then we go to the next one, which is a sum of infeasibilities method. And so the previous one you should think of as kind of roughly analogous to an L infinity norm. We were minimizing the maximum constraint violation. Now I'm going to minimize the sum of the constraint violation. The constraint violation is actually defined as this. It's Fi of X sub plus, right? If that's 0, it means you satisfy that thing. Otherwise, this is the amount by which you have violated the constraint, right? And so what this says is, instead, what we originally did was we did this. We minimized the max over I of these. I mean, this didn't matter, right? Right? Now we're going to do the following. We're going to do the sum. And before we even do this, I want some guesses about various things. These are non-negative numbers. A sum of non-negative numbers is basically the L1 norm, right? I mean, this is obvious, right? And when I minimize an L1 norm, what typically happens? You're going to get sparsity, right? And so this actually starts getting super interesting, right? Because what it is you say, I'm trying to design this, this thing, and you gave me 50 specs. And you go, bad news, can't be done. It's not achievable. And I can prove it, by the way, right? Because you can produce a certificate or a theorem of the alternatives, a certificate showing it. And they'd say, yeah, but we got to do something. We got to build this product or something. And you'd say, that's fine. Here's what I did. I did find something that satisfies 47 of your 50 constraints. Everybody got that? So, and that's what you would see here, which is really cool. And here's a picture. We can take a look at this. Oh, here's an example. This is actually the margin in your constraint. So you want to push this to be above 0. This failed. It's infeasible. You stop there. And just as we guessed, a whole bunch of them are lined up at this worst point, which is minus 0.2, or I don't know, whatever it is, 0.2, right? Okay, this is what happens when you do a sum of infeasibilities. And it's really cool. What it says is, 55 of your FIs are tight. Actually, these are all ones. They're slack, right? It's your whatever Fi of X is actually negative for these. And then you have a handful here which you can't satisfy, right? And so again, this is just our old friend, the L1 sparsifier here. It's kind of cool, right? This thing. And these are also already quite useful, right? In various applications that I've seen. So, okay, does this make sense? Here's an example. So you have just a family of linear inequalities. So it's a polyhedron, but I have a delta, a parameter gamma, and it's chosen so that when gamma equals 0, the polyhedron collapses and has 0 volume. when gamma is negative, or less than or equal to 0, well, it's not it's when it's negative, it's infeasible, and when it's positive, it's feasible, and you're just scaling the right-hand side, so the polyhedronous is growing, right? And now what we can do is we could use the basic phase 1 and stuff like that, and look at the number of steps it takes to either find a point, right, in the first case, so here's what it looks like. It's actually super interesting. So it looks like it takes like 40 steps unless you're right at the boundary of between feasible and infeasible. And that's the only, in fact, you have to adjust the data very carefully to get more than, whatever, 30, 40 steps to do this, to solve this phase 1 problem. But you can do it. I mean, but what it says in practice, it just doesn't happen, right? Oh, this is showing you the zoomed in version. Actually, these are sort of interesting, right? Because over on the left, you would say, this is taking only 30 steps. You'd say, why? Because it's infeasible, but there's a lot of certificates of it's obviously infeasible. It's easy, so it doesn't take many steps to prove infeasibility. This is like the polyhedron is over here on the right. The polyhedron is so big, it doesn't take very long to find a feasible point. And then the only time this increases is when you get right between the boundary of what's feasible and not feasible, right? So that's that's where it goes up like that. That's what it looks like. So, okay. So that's a picture of that. What we'll do is we'll just start talking about this, and we'll finish this up next week. But it's actually really quite cool. So we're going to assume that F0 is going to be, and the FIs are going to be, well, actually, it's actually the barrier. I want TF0 plus phi to be self-concordant, right? So that's the requirement. And there might be some, like, here's a maximum entropy problem with inequality constraints. And it turns out that's not self-concordant. Again, you don't have to know this, but when you put in the x bigger than or equal to 0, you add a log barrier, then it becomes, that's a redundant constraint, that x bigger than or equal to 0. That's completely redundant because this objective, its domain is x has to be bigger than or equal to 0. So this is completely redundant. But when you add that redundant constraint and you work out the log barrier, which is just negative sum log xi, then that function becomes self-concordant, right? But what I should do is I should preface all of this by saying what you're going to see is super cool, but it is not at all clear what its practical implications are, right? That is not clear at all. Its theoretical implications are very clear. Practical ones, not so much. So, and it's very weird, actually it'll change every couple of years, right? People will implement solvers which are actually use self-concordant barriers and all that kind of stuff and actually agree with the theory. But then they'll find something that just makes it a lot faster. And they're like, we don't care. Then the theorists will catch up a few years later and write something about it. Anyway, so there's just this oscillation where it kind of goes like that. But it's not at all clear, But I have met weird people who've said things like, they said, what barrier you're using, and you'd write it down, and someone would say like, oh my God, that's not self-concordant. You're like, the algorithm complexity police aren't here, right? So is there an algorithm complexity warrant for your arrest, or what are you worried about, right? Anyway, so, yeah, but nevertheless, it is very cool, the analysis. Okay, so let's take a look at it. It's actually just completely insane. It goes like this, right? So remember what it is there's two terms, right? There's basically the number of centering steps, but that's just like log 1 over mu. Like that's what it has to do with, right? Mu is this is how aggressively you walk along this central path, right? So that's in fact, people call that the homotopy parameter, right? It's how fast you increase your homotopy parameter, right? Okay, so the question is, how many Newton steps does it take if I'm on the central path, I increase t by a factor mu, and I have to calculate the new point, right? That is once we know if we bound that number, that's the number of Newton steps That's the maximum number of Newton steps you can take in one of these centering steps, and you multiply that by basically log 1 over mu, and you get your total number, your total count. Everybody got this? Okay, so if you remember what that looked like, it looked like this, and this sounded kind of weird. Basically, the number of steps looks like something like f of, let's say, x0 minus then f of, x star, like this, divided by some number. Did I write it out here or something? Yeah, I called it gamma there, right? And then plus a constant, right? It's not really a constant. The constant is really like a log something or other, but basically it's fine. It's 5 or something, or not even 5, right? So I don't know if you remember this, but this is if a function is self-concordant, this is the number. Actually, this is the same. The classical analysis gives you the same thing. It's just that C and gamma depend on all sorts of things that you would never know and are not affinely independent. But if F is self-concordant, we actually know what this, we know numbers that are valid for this, okay? Now, there is this embarrassing thing, which is someone says, what's the maximum number of Newton steps it's going to take? And you go, well, it's this. And you go, yeah, but how do you know this, right? And so it's very embarrassing because you'd say, oh yeah, no problem. To bound the number of Newton steps, all you have to do is first solve it using Newton's method. Then you know this. Then you subtract this and divide and add that, right? And you're like, dude, what? I just solved it. I know the exact number of Newton steps now, so I don't need your stupid bound anymore. Is everyone following this, right? So, I mean, it's reasonable, right? But you can even imagine what's going to help us here. Because this bound is a bound if you had a lower bound on that. So do you think we have a lower bound? Where do you imagine a lower bound on the optimum value something's is gonna come from before you've actually solved it? So should we say it all in unison or whatever? But you get one guess. Go ahead. Duality is gonna do it. Okay, so that's the highlight of the story, and we'll complete this next time.